Thanks everyone for coming back. We've had a short interlude, so we now have Daping Weng, who will tell us about cluster algebras for rainbow closures of positive braids. Please go ahead.
Yeah, thanks. Thanks for the invitation. Very happy to speak at this conference, this seminar, sorry. Yeah, so here's the plan of my talk. I'm going to talk about the first motivational definition of this this Bott-Samelson cells, which is also a way to understand this this moduli space of sheaves that Jae mentioned. The second part, I'm going to talk about how to get a Legendrian weave from such a Bott-Samelson cell. And then I'm going to talk about cycles and quivers and mutations in more details. So Jae touched on that already, but I'm going to show some pictures and describe a more detailed procedure how to obtain them. And then on the part 4, I'm going to give a crash course on cluster algebras. It's going to be a very short and a lot of details hidden away kind of a crash course. But if you're interested, I'm happy to talk to help you afterward. And then the last part, I'm going to say how to see the cluster structure using Legendrian weaves. So let me start the first part. And during this talk, at any point, if there's any question, please let me know. I'm happy to answer. And sometimes I may just overlook the chat. So yeah, just feel free to interrupt and ask questions. So first part, what is this rainbow closure in the title? So rainbow closure of a positive braid beta is this a Legendrian link with this front, right? So you put the positive braid beta down here, and then you close it up in this way. Right. So note that this is slightly different from the -1 closure that Jae showed, and I will say what the difference is. The big difference is basically you have 2 half twists on either side, right? So if you instead of beta, if you put 2 half twists on either side, or 1 half twist on either side, and then do the -1 closure, they're the same thing. So this is what we call the rainbow closure. And there are many algebraic invariants one can associate with this Legendrian link. And one such thing is this Kashwala-Shapiro moduli space of rank 1 sheaves in R2 with microlocal support on the Lagrangian. So Jae described it as a category, but then you can actually take objects from that category and study the moduli space of those objects, and that give you a moduli space. And in the case of rainbow closures of positive braids, these objects can actually be described in a very down-to-earth way. So let me just give you one example. So this is a trefoil. It's the positive braid is 1, 2, 1, 2, and you close it up, get a trefoil. A point in this moduli space is essentially the configurations of a bunch of vector spaces with a bunch of linear maps between them. You always associate 0 to the unbounded region. And then every time when you cross a strand, the rank increases by 1 or decreases by 1. So that's why you see a 1-dimensional vector spaces here, 2-dimensional vector spaces here. This is the 3-dimensional vector space in the middle, and then 2, and then 1, and then it's back to 0. And now you across each strand, you also have a linear map connecting them. And there's some condition that I'm going to say as well. So the conditions are across each crossing, you need an exact sequence. So this C goes into direct sum of these 2 C2s, goes back to this C3, right? This has to be exact, right? And another condition is that across each cusp, no matter whether it's left cusp or right cusp, when you compose the 2 maps, you should get the identity map for this between these 2 C2s. Well, they are actually the same in the same region, so you can identify the stocks, and this composition should be an identity map. Okay. Did I already have some? Oh, sorry, I just saw the chat has some comment. Okay, good. Right. So now I claim that this data is actually equivalent to a bunch of flags. How do I see a flag? Well, the flags are going to live inside this C3 in the middle. And the way I construct a flag is by looking at this sequence of maps. So you have a dimension 0 space and a dimension 1 space and a 2-dimensional space and a 3-dimensional space. So this chain of linear maps will describe you a flag in C3. So I'm going to call this F1. And then by moving to the C next door, you're going to get another flag. So this will give you a C2. So note that this C1 and C2, they differ at this quadrilateral here. And by the because of the exactness condition, this 2C has to be transverse inside the C2, right? So that means that these two flags, most of the subspaces are the same except for the one-dimensional subspace, and the one-dimensional subspace have to be different, right? So this is this is a notation that I'm going to use. It's going to be an arrow with an S1 here telling you that these two flags differ at dimension 1. So I should warn that this is not a map. This symbol is not telling you there's a map from F1 to F2. This symbol is just telling you that these two flags differ at the one-dimensional subspace. Okay. So by doing this, I actually get a bunch of flags. So there's F1, there's an F2, there's an F3, there's an F4, and there's an F5. And the relative position are given by the positive braid. So these two flags, they differ at dimension 1. So there's S1 here. These two flags differ in dimension 2. So there's an S2 here. These two flags differ in dimension 1. So there's this S1, and this is the S2 here. Right, so you get this chain of flags with prescribed relative position given by the positive braid beta. Now, I actually have another flag at the top, right? How? Well, there's a chain of maps in the top. Well, the rank decreases. So it's not exactly a flag yet. Well, but you can take kernels, right? So you can take the kernel of this map from C3 to C2, that gives you a one-dimensional space. And then you take the kernel from C3 all the way to C, that gives you a two-dimensional space. And take the kernel from C3 all the way to 0, that get you a three-dimensional space. So that gives you another flag. And then the relative position, the condition on cusps that I described earlier would tell you that this flag is actually transferred to this flag, like complete transverse, right? Because the image here has to be transverse to the kernel in order for this map to be identity, and so on. Like this image here has to be transferred to the kernel here in order for this composition to be identity. So therefore, I'm going to use the symbol W0. So W0 is inside this symmetric group. This is the longest element, and this longest element is normally denoted by W0. So this is like the most way of transversality you can get. So I'm going to just use this symbol to tell you that this flag is complete transverse to F1 and also complete transverse to F5. Okay. Any questions so far? Okay. So this object, accidental, before I even got into this symplectic context, I started it in a different context from a representation theory perspective. And we called it a Bott-Samelson cell because it came from the Bott-Samelson resolution of super varieties. And we realized that, well, we first, in this paper, we studied the cluster structure and did something with it. But then later we realized that this is exactly the same as this moduli space M1, this Kashwara-Shapira moduli space of sheaves with microlocal support on lambda. But also it's actually also related to this braid variety, which Jose is going to mention. And the relation is that this beta, this positive braid, you need to put another delta half twist here and then consider the braid variety. And they're actually also the same thing. So this Bott-Samelson cell actually occur in many different places. But I should also say that this Bott-Samelson cell is stacky in general. So if you want to get rid of this stackiness, you would need to put some decoration on it. And this decoration, in the end of the day, the decoration is basically, so you have a flag and you have subspaces inside the flag, and you basically put a top form inside each subspace. And then you consider, so each flag is now just a sequence of top forms. One is the wedge of the next one is the wedge of this one with something else. So a bunch of top forms, and you also need some compatibility condition. So this is what this decoration is. And from a a more geometric, so more symplectic perspective, it's the same as giving some sort of trivialization of the local system at the boundary. So I will say more about this later. All right. Yeah, so we proved that it's a cluster variety in that paper, but then using Legendrian weaves, you can actually give a symplectic interpretation of this cluster structure and then draw a closer connection between Bott-Samelson cells and this moduli space of sheaves that we considered. All right, so this leads me to the second part. So in this part, I want to tell you how to actually draw a weave for this. So I'm going to start with the same the Bott-Samelson setup. We have a chain of flags here given by the positive braid beta, and then you have one flag that's transverse to both of the first one and last one. Okay. For simplicity, let's just take the trefoil example that we saw. Right. So at the bottom, you have 5 flags. So you have 1, 2, 1, 2. So that's the positive braid beta. And then on the 2 sides, you have 2 flags that are general positioned. So you take this reduced word of W0. So in this case, it's so you are in the symmetric group of 3 elements. So the longest word is going to be 1, 2, 1 or 2, 1, 2. It's up to you. I'm just going to choose 1, 2, 1 here. So I put the 1, a 2, a 1. By the way, my convention is that blue is sigma 1 and red is sigma 2. So it's not exactly the same as what Roger used. But let's just keep track that this is X sigma 1, this is sigma 2. Okay, and then I'm going to deform my disk into a rectangle like this. Okay, topologically you can do that. Next, I'm going to just take this W0 and I'm going to try to extend it to the right. And then there's a sigma 1 down here, so I need to somehow join them together. So I join them with this trivalent vertex. Okay. And then by the next, if I just continue with this W0 further to the right and try to join this red one, it wouldn't work because there's a blue one here. So what you do is you need to do a change of braid word. So you have to change the 1, 2, 1 into a 2, 1, 2. And you can do that because we have the hexavalent vertex. So hexavalent vertex is what allows you to change it into different reduced words of W0. So once you do that, you get this picture here. And the next one, it's a blue one again, so I have to do another change of braid word and so on. And in the end, you get this picture here. Okay. And I should also say that this picture is not exactly the same picture that Roger showed you, but then if you tilt your head 90 degrees to one side, so if you think of this as the top, this is also the top, so these 2 sides are the top and this side is the bottom, then you see a Del-Marzou weave. So I think this is what's called the right inductive Del-Marzou weave in their paper. Yeah, so you have to kind of see it the sideway. All right. So as Roger mentioned, this Legendrian weave describes an exact Lagrangian filling for the rainbow closure of the positive braid, because if you look at the boundary of this disk, you're going to see beta and a delta and another delta here. So get a -1 closure of beta delta square, which is the same as the rainbow closure beta. Any questions so far on how we get this weave? All right. So here comes the next part. So how do I find the cycles and how do I get the quiver and the mutation? Okay. So we can obtain topological information for the exact Lagrangian filling from some combinatorics on the Legendrian weave, right? So for example, as Roger mentioned, the Euler characteristic of this exact Lagrangian filling is going to be the number of colors plus 1, right? So that's the number of sheets inside the front, the wave front. So this is the n-to-1 cover of the R2, and then you minus the number of trivalent vertices. And you can also find representatives of 1 cycles on the Legendrian weave. Okay, so for example, if you see a weave line here, the spatial front has 2 sheets crossing. So when you do the lift, these 2 sheets are going to give you 2 lifts. So each point generically inside the weave, inside the weave line, you're going to get 2 preimages. Okay, but then, so each point it gives you 2 preimages, so that you get 2 lines. But then when you come close to a trivalent vertex, because the tangent is flat at those two trivalent vertices, the two preimages is going to merge. And that's how you see a cycle there. So the preimage of this weave line gives you a cycle on the nose. And by using some canonical orientation on the Lagrangian filling, you actually orient this, give an orientation on this cycle as well. And as Roger mentioned, this cycle bounds a Lagrangian disk in the complement of the filling. Right? And the Lagrangian disk is basically you just go through the cotangent direction using the same image, same point in the front, but then just sweep the cotangent direction. All right. And then, as Roger mentioned, there's also a branching behavior at hexavalent vertices. So at a hexavalent vertex, a cycle could either go through or branch. So let me also show some pictures. So the spatial front of a hexavalent vertex, you can imagine as you take R3 and take the coordinate hyperplanes in R3, and generically, if you imagine yourself as standing in the positive octant and looking towards the origin, generically, you're going to see three sheets, right? But then the sheets are going to cross each other at the coordinate axis, right? So in particular, along each positive half of the coordinate axis, you're going to see the top two sheets cross. And then along the negative half axis, you're going to see bottom two sheets cross, right? So you're going to see this picture here. That's a local picture of this hexavalent vertex, of the wave of the spatial front of this hexavalent vertex. Now, say the cycle just goes straight through. So what that looks like on this local picture is that you're going to see that it goes through one sheet, say the vertical sheet from left to right here, but then when it comes back, it actually goes through the horizontal sheet from right to left along this weave line, along these two weave lines. Right? So that's the local model for this going straight cycle. On the other hand, if it branches, say on these three red weave lines. So the cycle locally behaves like the following. So it goes in here in the horizontal sheet, but then it bends towards this direction. And then comes back on the vertical sheet and bends up. And then comes back from the other vertical sheet, and then it bends to the right. Okay, so you can see this. You're going to see this this branching behavior at this hexavalent vertex. Okay, we call the one cycles that combinatorially described by a tree on the Legendrian weave, called them Y trees. And if a Y tree only have one weave line edge inside, we call it a short I cycle. Okay. Right. And furthermore, since the exact Lagrangian filling is equipped with an orientation, there's a skew-symmetric pairing between the one cycles given by the algebraic intersection number. And algebraic intersection number between cycles that you can draw on the weave actually can be computed combinatorially. Right? So for example, you have three cycles that end at this trivalent vertex, then the intersection pairing between the green one and the orange one is going to be 1, meaning that the orange one with the pair with the green one is going to be -1. So I'm going to count the signs as well. So then I can use an arrow to represent this pairing. So when I go from the source to target, I get a +1. So the green pair with the orange is +1, orange pair with the green is -1. So you actually get this oriented 3 cycle at each trivalent vertex, counterclockwise oriented 3 cycle. Right? Or the orange one with the purple one is +1, and purple one, green one is also +1. Okay. On the hexavalent vertex, the only way you can get in the non-trivial intersection numbers is when the cycles go straight through. Right? When they go straight through, then you're going to have some intersection numbers. And the intersection numbers, this orange one paired with the green one is +1, the green one paired with the purple one is +1, and the purple one paired with the orange one is also +1. Okay? So this is the only case where you're going to see intersections. If you have a branching Y cycle at the hexavalent vertex, then there's no intersection at all. right? So therefore, given a collection of 1 cycles on the exact Lagrangian filling, we can build a quiver whose vertices are the 1 cycles and the arrows are given by the intersection number pairing. Okay. So for example, this trefoil example we just saw, its Euler characteristic is -1. That means it's it also has 1 boundary component. So the genus is also 1, right? So it's a 1 boundary torus, right? 1 puncture torus. And then I'm going to show you 2 cycles here. So one starts at this trivalent vertex and goes straight through the hexavalent vertices and then end at this trivalent vertex. So there's 1 cycle here. Another cycle starts at this red one and goes straight through and ends at this red one again. Okay, and note that these 2 cycles, they both go through this hexavalent vertex here, and they go straight through, so they intersect. And according to the rule, there's 1 intersection. Right? So you have a green vertex in the quiver representing this cycle, and a purple vertex in the quiver representing this cycle, and these 2 cycles intersect. So you get an arrow in between them. Right? So you get an A2 quiver in this case. Any questions so far? All right. So we observed that for any positive braid, the cycles, you can actually construct long cycles between every 2 adjacent crossings on the same level, right? So by generalizing this observation, right, if you see a braid and then you see 2 crossings on the same level, so these are both sigma 1, these are both sigma 2, right? Say if you have a 4-stranded braid, then you could have sigma 3, and between every 2 adjacent crossings of the same level, you can always find such a long I cycle, right? Going from 1 and then go into the weave and then just go straight across every hexavalent vertex, and you end at the next crossing on the same level. Okay, so that gives you a bunch of 1 cycles, and you can actually show that these 1 cycles do form a basis. There are enough many of them, and they'll give you a basis of the H1 of the filling. Okay. And by working out the combinatorics in detail, you can actually write down a rule without ever referring to the Legendrian weave. So the rule is, like I said, between every 2 crossings on the same level, you get a vertex. Right? So I'm going to get a vertex here, I'm going to get a vertex between these 2, I'm going to get a vertex between these 2, and a vertex between these 2, and so on. And then for the vertices on the same level, you're going to see an arrow going from the left to the right, right to the left. Sorry, I forgot which convention I used. Going from right to left, but then across vertices on different levels, if you see them separated by a strand that goes from left to right. So these 2 are separated by this strand here. So go from left to right, and this go from left to right. Okay, so you get this. So you can construct this quiver by just looking at the front. So note that these 2 will not have an arrow because they are separated by both this slanted strand and also this side. So they will cancel each other and there's no arrow between them. All right. And there's actually a JavaScript calculator that I wrote. It's for a separate project, but actually it's also used for computing this quiver. So let me just show you. Show you real quick. So you can actually find this calculator on my website. You can just enter the number of strands, say 4, and then enter a braid word 1, 2, 3, 2, 1, 2, 1. 3, 2, 2, 3, okay. And then you hit draw. It draws you the braid and gives you the quiver right here. So this is the quiver. And if you want the cluster variables, which I will tell you in a bit, so these are the cluster variables. So right now they're written in what's called the ripcord coordinates. So this B is actually what's going to be the Z's in Jose's talk. Or in Roger's slides, but you can actually, if you just want to check and see if you get the exercise right, you can just use this calculator to check. Although there's some sign convention that you need to pay attention to, but I'm not going to say more about it. Yep. And then I'm going to go back to my slides. Any question on this? All right. Also, I should warn that this is not the case for braid varieties in general. So only for rainbow closures of positive braids, you can use this rule. For braid varieties in general, the cycle is actually not necessarily long I cycles, and you would typically see some sort of branching behavior, and sometimes even cycles they will be immersed; they're no longer embedded. Okay, so you'll see this in Jose's talk. Okay, so why do we care about these Y trees and I cycles? Well, there's a lemma that we proved that for if you can draw a Y tree on a Legendrian weave, there's a way to use weave equivalences to turn that Y tree into a short I cycle. So, but you have to pay a price of making other cycles more complicated. But if you have a Y tree, you can always shrink it down to a short I cycle. And then once you have a short I cycle, you can do this topology surgery, and on the weave level, it is just taking this short I cycle in the middle and shrinking it and then expanding it in the other way. But you can also see this on the kind of see it on the Lagrangian surface, right? So this cycle, this cycle bounds a Lagrangian disk in the complement. So this is the blue disk here. So when you do the surgery, you will shrink this blue disk down to a point, okay? And also I drew some cycles as going transverse to this blue cycle here. And those cycles will also change under this surgery. So you shrink it to a point, and then you're trying to resolve this singularity, right? Podologis tell us that there are only two ways to resolve it. One is go back to the way you begin, and the other way is to get a new surface that look kind of exactly the same topologically, but symplectically they're different. And in particular, I purposefully draw the cycle in the opposite direction. So you should really think that these two cycles are kind of oriented oppositely. And the green cycle will not change, but then the red cycle get then twisted. So in some literature, people call this the half Dane twist. But let me just say that this is not a Dane twist. A Dane twist, there's something else called half Dane twist, but this is not a Dane twist. What this half means that only half of the cycles get Dane twisted. So it's not a Dane twist at all. Right? So depending on how the cycles intersect, some of them just remain unchanged and the other ones get Dane twisted. All right. So on the quiver level, what happened during a weave mutation? So a weave mutation actually corresponds to what's called a quiver mutation. Okay. So I'm going to color the possible cycles in different colors. Right. So in particular, on the surrounding, I'm going to color them the same way as before. Then if you follow the rules to draw the quiver, you see that this side, you're going to get a oriented three cycle here. On this side, you're going to get oriented three cycles this way, okay, on the quiver. And after you do the mutation, you're going to see this quiver here, okay? And these two quivers actually differ by what's called a quiver mutation. So let me tell you the definition of quiver mutation. So in general, suppose you have a quiver that does not have any one cycles or two cycles, oriented one cycle or two cycles. So oriented one cycle is a loop, right? It goes from a vertex back to itself. And oriented two cycles, you have two vertices, and then you have an arrow going this way and then come back to the same vertex. So that's an oriented two cycle in a graph. A mutation, suppose your quiver does not have any of those, right? So for example, this quiver here, right? I mean, there are two arrows between these two vertices, but they're not oriented, right? So they both point from this one to that one. So that's okay, as long as it doesn't go back. Okay? Suppose your quiver does not have any of those. You can mutate this quiver at the vertex K to produce a new quiver, right? So I color this vertex K that I'm going to mutate in red. And this mutation goes through three steps. One, for any two-step path that goes through the mutating vertex, you add an arrow, right? So for example, here you have one two-step path here, so you add one arrow. You have another two-step path, so you add another arrow. Right? So for any two-step path, you add an arrow. Then you reverse all the arrows that are incident to the mutating vertex. So you reverse them like that. And then 3, you just get rid of a maximal subset of oriented 2 cycles. So here you actually see two cycles. But then once you get rid of one of them, the other one disappears. So you can get rid of either one of them. And then you get this quiver here. Okay, so that's how you do quiver mutation. So this quiver mutation is actually, people study this in representation theory, quiver representations a lot. It's a generalization of this, how Gabriel proved the Gabriel's theorem in decomposable representations, quiver representations. Any question so far? Okay. All right. So next part, I'm going to give a crash course on cluster algebra / variety. Okay. So since this is a more geometric-oriented audience, I'm going to give a more geometric-oriented introduction. So let's first do a review of the toric case. So consider a z to the n as a character lattice of an algebraic torus. Okay, so c star to the n. So a basis of this lattice M will give you a coordinate system on T, and you can identify the ring of regular functions on this algebraic torus with the Laurent polynomial ring in n variables. So Cx1 to xn. So each variable corresponds to a basis element in this basis that you chose. Okay, and I mean, in some sense, you can just think of this basis as x1, but then the power tells you whether it's v or minus v. So you just basically write the addition multiplicatively. Okay. And then if you do a change of basis, the corresponding Laurent polynomial ring are related by a Laurent monomial change, right? So suppose, say the new basis element is a sum of v1 and v2, then x1 prime is going to be x1 times x2, right? Things like that. Right. So this kind of Laurent monomial change is an isomorphism between Laurent polynomial rings. Okay. So now if you consider a rational fan consisting of regular simplicial cones in Rn, each chamber will give you a, so since they are simplicial, so each chamber will give you a basis of this Zn, and this basis is going to give you some way to visualize this coordinate ring as a Laurent polynomial ring. And if you go from one chamber to another chamber, you're basically doing a monomial change. So the Laurent polynomial ring are isomorphic under this wall crossing. Okay? So they give you an identification of all those algebraic tori. And in the end, you get a single torus, which is what you expect, right? In the toric variety, there's only one single torus sitting inside in the middle, the biggest one, open one. Okay, so this is the torus in the toric variety. Okay, so the way to get, so the cluster variety, right way to think about cluster variety is to just think about this torus in like toric variety, but then you deform it a little bit. So no longer have a single torus, but you have a bunch of tori. So now let me say the cluster case. So cluster varieties were introduced by Fock and Ganstroff as a geometric enrichment of cluster algebra introduced by Fomin and Zaravinsky. So like I said, in contrast to the toric case, you no longer identify the Laurent polynomial rings between chambers. Instead, you not identify them, but you relate them birationally using mutation maps. Okay. So more precisely, to each chamber, a Laurent so you associate to each chamber a Laurent polynomial ring and a quiver, right? So here's where the quiver comes in. The quiver tells you how two adjacent chambers are related. Okay? So across a wall separating two chambers, the quivers will be related by mutation at the differing vertex, because the two chambers, they share a codimensional one wall. So only two rays are different. So the quiver will differ at a mutation at that vertex. And then the way you relate the two Laurent polynomial ring is by this birational transformation. Okay? So it's no longer a Laurent monomial transformation, it's a birational transformation. Okay, and then you take all these tori, one for each chamber, and then you glue them via these birational transformations. The union of these tori is the cluster variety up to codimension 2. So the reason I put this clause here is because generally speaking, when you take union of a bunch of open stuff, the result is not necessarily a variety. So you have to kind of compactify it a bit. But algebraically, what that really happens is that you take Laurent polynomial rings as a subring inside the fraction field of rational functions, and binomial transformation will map one to the other. But then you take the intersection of all these Laurent polynomial rings, right? Once you take the intersection, you can take the spec of it, and that will give you the cluster variety. So the corner ring of this cluster variety is called a cluster algebra. Well, so there's also a clause here. It's really what's called upper cluster algebra. But in many cases, in particular for the braid varieties and this Bott-Samelson cell, they actually coincide. So there's nothing wrong to say cluster algebra in this case. All right, so this is an example. So this is basically the same fan that I showed you earlier, but now instead of a monomial change across walls, these are going to be rational change, right? So I'm going to identify this Laurent polynomial ring as x and 1 plus x over y, right? And when you go across a wall, the quiver differ by mutation like this, okay? So, and the amazing thing is if you mutate 5 times and come back, you get back the same Laurent polynomial ring. So, and once you intersect all of these Laurent polynomial rings, you get what's called the A2 cluster algebra, because this is the A2 quiver. Right? Any question? Yeah, so this cluster algebra, actually, this is a very primitive definition. There are a lot more detail that I didn't give out, but Fomin and Williams and they're working on Lauren Williams. They're working on a textbook, so there's a very good reference to if you want to learn more about cluster algebra. Yeah, I recommend to read that textbook. Yeah, it's available on arXiv. It hasn't been published yet, so that's a good thing. All right. Yeah, so some terminology. So the elements associated to these primitive vectors inside chamber is called cluster variable. So this x, y, this is 1 plus y over x, this guy and this guy, they are cluster variables. And the collection of cluster variables belong to the same chamber is called cluster. So this x and y, these two is called cluster. Y and 1 plus y over x, that's a cluster, and that's a cluster. Okay, so there are 5 clusters here, and there are also 5 cluster variables. Each cluster contains 2 cluster variables. So one important theorem in clusters theory is the Laurent phenomenon. It tells you that any cluster variable can be expressed as a Laurent polynomial with respect to any cluster. Okay, so this is a highly non-trivial theorem. So for example, imagine this, right? Say you have these 2 cluster variables, and then when you mutate, say you want to mutate this one away, right? A priori, what you do is you take this one, you add 1 to it, because there's nothing pointing towards this vertex here. So you add 1 to this variable, and you divide by this one. A priori, there's no way to see that the resulting thing is a Laurent polynomial in xy, right? But surprisingly, you get 1 plus x over y as a result after you go through a simplification, and that's indeed a Laurent polynomial in xy. So this theorem is highly non-trivial. but that's what one of the basic one of the important results from cluster theory, and consequently, geometrically, that's telling you that cluster variables are regular functions on cluster variety, because cluster variety is obtained by gluing a bunch of tori. And if a cluster variable can always be written as a Laurent polynomial with respect to any cluster, that means that it's always a Laurent polynomial in respect to each torus inside this chart, inside this atlas, right? And therefore, it's a global function. Right? So this is what Roger was hinting at. Like there's some special functions on this variety that are global, right? They may be just constructed locally on some chart, but they can be extended globally. Right. Another theorem is called a starfish lemma. So in nice cases, there's some technical assumption that I'm not going to say, but in good cases, in particular, including the braid variety case, a cluster variety is covered up to codimension 2 by a finite amount of tori, namely the initial torus that you fix, and you mutate at each vertex, right? You mutate one step. And you get, if you have n vertices in your quiver, you're going to get n tori. So this n plus 1 tori will cover the whole thing up to codimension 2. So that's another important result. So the statement that these functions can be extended to the whole variety, it suffices to check that it's extend over to these once mutated guys. Right? So that's also another important result. It's proved by Bernstein, Fomin, and Zarvinsky. Okay, one more thing. Just like the toric case, the combinatorial data can, in some sense, better encode it on the dual side, right? So if you know tropicalization, right, this is the right way to think about it. The dual side is actually, just think of it as a tropicalization of your variety, right? So that's why I'm going to take the dual lattice n, and then we assume that n is equipped with a z-valued skew-symmetric form. Then each chamber is going to correspond to a basis of n, right? This basis is called a seed. And then a quiver Q can actually compute it by using this skew-symmetric form that's already on n, and take the skew-symmetric form of EI and EJ. That will give you a matrix, and this matrix tells you number of arrows from I to j. So that's how you get the quiver. I just saw that there's a comment on chat. I hint on what type of conditions being asked when you say good cases. Starfish lemma. Yes. It's called the full rank condition. The quiver needs to be full rank. So in the quiver, so normally you would allow frozen vertices as well, and so frozen vertices are vertices in the quiver that you're not allowed to mutate that. Then you take the rectangular submatrix spanned by the mutable vertex versus all the vertices, and you ask that part of the exchange matrix to be full rank. So once you know that your matrix is full rank, then this starfish lemma holds. So that's the technical condition. All right. So now quiver mutation can be understood as a change of basis in n. Right, so that's all it is. You change from one basis to another basis via this formula. So this formula actually happens to be the tropicalized version of what's called a cluster X mutation. Right? That's why I had the word tropicalization here. Right? That's really what's happening. Okay, and this symbol n with a little bracket and a little plus here means that you take n if n is positive and take 0 otherwise. All right, so this leads me to the last part of my talk, the cluster structure on Bott-Samelson cells using Legendrian weaves. Okay, so for simplicity, I'm going to assume for the rest of the presentation that the rainbow closure is a knot. If it's a link, you have to put these base points in, and it makes the story a little bit more complicated. Right? So the link case is actually, Roger and I had this work, and we studied this link case as well, but for simplicity, let's assume that's a knot. So I described earlier, there's a way to draw an initial Lagrangian weave from the rainbow closure. And to obtain the cluster structure, like I said in the previous slide, you need a lattice and you need a skew symmetric form. So the lattice is going to be the first homology of your exact Lagrangian filling with z coefficients. Right? And then you have intersection pairing between one cycles, that's your skew symmetric form. And you set and then you also need an initial seed. You need a basis of this n. So this basis will be these long I cycles that I described. Okay, we said earlier that between two crossings of the braid on the same level, you're going to get a long I cycle. Right? Take those cycles, they will give you a basis for the first homology. Okay, so by following the cluster recipe, you know that the initial cluster variable should correspond to dual basis of this thing, right? So remember, the cluster variables live on the M lattice rather than the N lattice. So you need to take the dual lattice. So what's the dual lattice to the first homology? Well, the dual lattice is the relative homology by Poincare duality. Okay? So I'm going to consider this relative homology of the exact Lagrangian field relative to the boundary, but the boundary is exactly the Lagrangian link, that's Lagrangian knot in this case. So you consider this H1 lattice, and you should be able to represent the dual basis as relative one cycles on the Lagrangian on the exact Lagrangian filling. So let me describe how you do that. So thanks to the way that the initial Lagrangian weaves is constructed, you can actually describe them by the projection on D on the disk with additional specified intersection number. So for example, consider this truffle case that we presented earlier. We had two one cycles here. Okay, I will claim that this dashed line together with the intersection number 1, 1, and 0 will tell you a relative cycle that's dual to the purple cycle, and will intersect the purple cycle once and intersect the orange cycle 0 times. So how do I see this cycle? Well, you take a cross section of your spatial front at this dashed line, you're going to see this picture here, right? I said earlier that the red weave line is sigma 2, the blue weave line is sigma 1. So you're going to see a crossing at level 2, and a crossing at level 1 here. So this is a cross section. So you take your spatial front in R3 and just slice it down this dashed line. The cross section will look like this. And then I'm going to look at these intersection numbers, and I'm trying to find a union of sheets that goes through the weave lines according to these numbers. So it shouldn't go through this line at all, right? So that's 0, and it goes through this line once, that's a 1 here and 1 here. And also I'm taking this with a sign. So going through it one time versus -1 time is different. So one time means it goes from bottom up one time. Okay. So it goes through this one time, goes through this one time. While this is not a unique representative, this is also a representative. Okay. So I also go through this one time, also go through this one time, but now these two sheets cross, and this goes through it one time, and this goes through it -1 time. So in total, it goes through it 0 times. So that works as well. So what I want to say is this does not give you a unique representatives, but all representatives are homologous, because that's what Poincare duality tells us. If you know a set of cycles, a basis, right, and you also know how a relative cycle intersect this, right, all the members of this basis, then you will know this relative cycle uniquely. Right? So they're all homologous. Okay, so similarly, I can also take a slice here, and I'm going to specify the intersection number 0, 1, 1, and I'm going to get this one, right? We'll intersect this 0 times, 1 time, and 1 time. Okay? So you get this relative cycle as well, right? So in general, right, if you have a braid put here, you can always slice it generically at some point, slice the braid. the cross section is always going to be some W naught, right? And then you can find the right number of intersection numbers so that you get a dual relative cycle that intersect a specific cycle once and everything else 0 times. So that's the construction. Okay, so after you identify this M lattice with the relative homology, right? This algebraic torus can have a new meaning, right? It is identified with the moduli space of rank 1 local systems with a trivialization along the boundary. Okay, so that's what this is. Right, so maybe I should say more. So the way you understand this is like H1 will tell you, right? So this local system, you just need to know how what the monodromy is along each cycle, as well as what the parallel transport is for a relative cycle from one boundary component, well, from one point of boundary to another point of boundary, right? But since we already have a dual basis of this guy, we can get functions using this. So for each relative cycle, you can associate the C star value function by parallel transporting the trivialization from the source through this relative cycle to the target. But then the target already has a trivialization there. So you can take the ratio of the two and get a C star number out of it. So that gives you a C star number on this moduli space. And that is those generators of the of this corner ring as a Laurent polynomial ring. Okay, and we call these functions the micro-local merodromies, right? So we call it merodromy because it's partial; it's not the full cycle, right? So full cycle will be a monodromy. If it's a relative cycle, we call it a merodromy. Yeah, and these are the initial cluster variables. Okay, and in the case of rainbow closures of positive braids, this data of trivialization along this Lagrangian knot is equivalent to assigning a non-zero form on each non-zero subspace in the flag Fi, right? So the way to see this is that when you look at the boundary, right, you have a flag and you have a 0 space, 1-dimensional space, 2-dimensional space, and so on, right? And then for each, they're separated by the strands of your knot. If you have a trivialization on each strand, then you can, so that trivialization gives you a 1 form at the bottom already. And then when you jump up to the next level, right, you can take the wedge of those two trivializations, give you a 2 form, and so on and so forth. So you can get a non-zero top form on each subspace of the flag. Okay? And this will satisfy this compatibility condition that we need for the decorated Bott-Samelson cell. So this algebraic torus naturally sits inside. Okay. And if it happens that your representative goes through a reduced braid word, so like this 212, then this merodromy can actually be computed quite easily. It's a determinant. So how? Well, it's basically you take what's called like a cross product of the things from the top from the source and the target, right? So you take beta v and you divide by this top form determinant, the dual of determinant and 1. So that's the ratio that you will be taking. But of course, the dual of determinant is the same as determinant of this 3 form, right? So you just take this v and this beta and wedge them and take the determinant. And because of that, all the initial cluster cycles are uniquely determined by the decoration you put on the boundary flags. Okay, and therefore they're all global regular functions on the initial cluster on the whole Bott-Samelson cell. Okay, let me also say how you see this from the Bott-Samelson side, right? So like I said, you have this configuration of flags, right? We may as well just fix this flag to be F minus and this to be F plus. So F plus is 0 inside span of E1, inside the span of E1, E2, and so on. And F minus is spanning en minus 1 en, and so on. And you can see that these two flags are opposite to each other because one is going from 1, 2, 3, and so on, and the other one goes from n minus 1, and so on down. So they are opposite flags. And for the remaining flags, you can parameterize them by using this braid matrix. So what this braid matrix is that you take this 2 by 2 matrix, Z minus 1, 1, 0, and then you can map it into GLN by a group homomorphism from SL2 to SLN, right? You can so this VI is the group homomorphism given by any simple root I. So you can map this in and you get the braid matrix, and you just act on this flag by the braid matrix and so on, and you get, this is a way to parameterize these flags. And then the relative cycles are going to go between these nodes, and according to this, what this crossing is, well, you get a certain number of intersection numbers, but then you use these intersection numbers to turn it back into a determinant. So each cluster variables can actually be realized as minus of some product of braid matrices, right? So if this I1 is going to be the I1 minor, so I1 minor meaning that you take the I1 by I1 submatrix on the upper left and take the determinant of that submatrix, right? So you take that, right? Well, that in this case just gives you Z1. But then the next step, right, you have the product of the two braid matrices, and then you take the I2 minor of it, right? So you get something else, right? And you can keep on doing this, and this will give you the initial cluster variables. And if you want to do a reality check, you can go to the JavaScript calculator that I had and run that computation, and that will exactly give you these cluster variables in the beginning. Okay? And except, I mean, it's written in BI instead of ZI. Yeah, so these ZI is actually, they also correspond to ripcords on your Legendrian links. Okay, any questions so far? All right, so next, let's talk about mutation. So like I said, right, in this Bott-Samelson case, all the cycles are going to be long I cycles, and then by using equivalences, you can shorten them to a short I cycle, and then you can perform a weave mutation, right? And once you do a weave mutation, you're going to get a new weave, which gives you a new feeling. Like, how do you identify the homology lattices of these two feelings? Well, you identify them exactly how you identify the cluster seeds, right? It's the change of basis. So you just identify gamma I prime here as these things here, right? These are exactly the cluster mutation, the tropicalized cluster X mutation. Right. Correspondingly, the rank 1 local systems of the two surfaces are related by the following birational map. Right? So this is the full cluster X mutation formula. Right? If you tropicalize this, you get exactly that. Right? So these are what's called the micro-local monodromies. So these have been studied by Shande, Truman, Williams, and Zaslow before, but they did not define the cluster A variables. These are the X variables. So there's a difference there. Right. And what about the cluster variables, the cluster A variables? So dually, the relative homologies are also related, right? And you can just dualize what the relation is for the cycles, and you get that if it's not dual to the cycle that you're mutating, then the relative cycles stay the same. And if it is the one that's dual to the mutating cycle, then you get a different formula. It's going to be this one here. So this is, again, the tropicalization of the cluster A mutation formula, like a product plus another product divided by something. And you tropicalize it, you get exactly this. And let me also remind you that in the tropical A, in the cluster A mutation, only one thing changes. That's exactly what we're seeing here. Only one relative cycle changes. All the other things remain the same. Okay. And correspondingly, the algebraic tori are related by the cluster A mutation formulas, and using to some very technical way, you can prove that these A primes are also regular functions. And the way you do it is by looking at how it extends to other boundary divisors of this initial torus inside the variety, and prove that these A primes can also extend. Okay. Right. So by verifying this is covered by the initial class torus and the once mutated tori, you can conclude from the starfish lemma that this Bott-Samelson cell is a cluster variety. And I think that's all I want to say for today. Yes. Thank you.
Thank you. Any questions? Okay, well, while people are thinking, I have one very naive question, and then maybe a not naive question, we'll see. My naive question is, you motivated the discussion at the very beginning with this toric variety picture. In particular, you talked about A2, and so you drew some fans, right? So there is an actual, so there's this combinatorics of this fan, and you can decorate it so that you can obtain from it this kind of cluster variety, and you can decorate it, well, you don't need to decorate it at all, so that you produce from it a toric variety. Is there any relation between these two that's kind of?
Yes, yes. So the decoration you put on to get the cluster variety. So this thing, let me just go to.
It's a long time ago. Sorry.
No, it's here. It's here. Yes.
Oh, so, yes. Okay.
Yes. In this thing, yes, you're right. So there's something I put on here to tell you how you cross the wall. So this combinatorial object is what's called a scattering diagram. It's actually introduced by Gross, Hacking, Q, and Kontsevich. And there's a version of the scattering diagram that you actually put in parameters on the wall crossing formula. And when you send the parameter to 0, that makes the wall crossing into identity. Right. So that's what's called toric degeneration of a cluster variety.
I see.
Cluster variety will have a toric degeneration. So for example, we can take this cluster variety as a variety. It is, I think this is a Del Paso 5 with 5 divisors removed, and then you can actually degenerate it into a 2 torus, a dimension 2 algebraic torus.
Is this some general phenomenon that?
Yeah.
Okay. I'll see if anybody else has any questions. I'm looking through the chat. Looks like. Okay, let me see. Looks like nothing. I have another question, which is kind of probably. So, in this, so you're studying, basically Lagrangians with boundaries that are two-dimensional Lagrangians with boundaries that are Legendrians. And you produce from this some kind of high-dimensional space, but some kind of linear space, these flag varieties and correspondences, whatever. Is there a candidate kind of mirror B side for these computations involving augmentation varieties? Which, by that I mean, we're doing some computation in like a symplectic 4-manifold. So is there some complex surface, maybe singular complex surface, maybe like something with a Lagrangian potential, where I could hope that, I could translate everything you're doing to something algebra geometric?
Yes. So in this workshop that Roger mentioned, the AIM workshop, this was actually one of the topics that were discussed. And I think we have made some progress in that. So in this braid variety case, you can actually construct the Landau-Ginsburg model, can construct a superpotential and run that program. Yes.
I see.
There is such a thing. Yes.
Good. Thank you. Okay. Anybody else have anything that they want to ask, add, comment? Okay.
Actually, I would just like to ask a question. In an answer to Mohammed's first question, you were talking about cluster varieties sort of as enhancements of toric varieties. Where could you read about that? Is there a nice reference?
Yeah, so there's a paper by Laura Bosinger and her collaborators on, I think there's a toric degeneration in the title, either it's in the title or in like one of the in the introduction. Yeah, it's toric degeneration of cluster varieties.
Okay.
Something like that. Yeah, Laura Bosinger.
Bosinger. Okay. Thank you.
Okay. Okay, so let's take a 10-minute break.